In this webinar, we'll show you how to enhance qubit control and readout system in a quantum computing system. We're going to demonstrate how to generate and measure process phase accurate pulses, pi over 2 pulses, as we stimulate various types of, or we stimulate a semiconductor based qubit, for example, and do a number of measurements on it. We're going to look at our RF analog to digital converters and digitizers, plus with the integrated FPGA based processing system language that I'll introduce today that we call decision blocks. Most of this presentation focuses around the capability of what we call the Proteus arbitrary waveform transceiver. This is a reasonably new instrument to the market. It's got RF digital to analog converters and analog to digital converter technology. I'm going to show you how to program the FPGA, make some waveforms, and how to create essentially a real-time low latency feedback loop. So here's the agenda. So we're going to look at our theoretical qubit and what types of measurements we're going to do on the qubit. We're going to look at the arbitrary waveform transceiver block diagram to understand how we can make better measurements on the qubit that we just talked about. Then we're going to talk about direct to RF signal generation, direct to RF signal acquisition, and then we're going to demystify FPGA programming using our decision block language, and then we'll conclude for questions. So this is what I call our theoretical qubit. This is the qubit in the center. Essentially, as you may or may not know, a qubit is a resonant oscillator, and you stimulate it with a certain frequency, and that frequency will either make the qubit spin up to a state or spin down to a state. You can control the number of states by using a Josephson's junction instead of an inductor here, and you generally generate some kind of shaped pulse, pi pulse or a pi over 2 pulse, with a baseband arbitrary waveform generator. Then you use a signal generator to get it up to the appropriate microwave signal, say 4 or 8 gigahertz, depending if you're doing control or readout. And then conversely, on the other side of the qubit system here, you do some amplification and a down conversion stage and do a measurement. What's not shown here is this qubit is usually in a dilution refrigerator and cooled down to a few millikelvins, as it's a superconducting circuit. So when we come out of the control system, it goes down, it's attenuated because you don't even want the warmth of the RF signal to heat up your qubit system. And then you come out of the dilution refrigerator with some amplification and be able to measure it. Typical measurements, we need to find the resonance of our qubit states, and so that's we would do a spectroscopy measurement. We want to be able to see how when we have the right frequency, see how it oscillates, how the electrons oscillate from one state back down to another state. So we do the Ramsey oscillation. We can measure T2 times with Ramsey interferometry, and of course the key measurement is to see how long we can maintain a quantum state with the T1 measurement. So these are all things that we would do using this shaped pulse multiplied to microwave and translate back down to RF measurement system. So traditionally this would be a signal generator here, another signal generator here, an arbitrary waveform generator here, and an oscilloscope here. And what we've done with our Proteus platform is managed to combine all those into a single unit, a modular unit, because of course you're going to have 1 qubit today, you might have 4 qubits tomorrow, you might have 72 next year, you might have 148 qubits a year after. So this here is a 4 qubit control system. It's about 2 inches wide and about 4 inches high, and this is what the architecture looks like of the instrumentation. So we have the on the signal generation side, we have RF DACs, and I'm going to cover what the difference between an RF DAC is and a regular DAC. We have some kind of output stage and output circuitry. Please, everybody, make sure you're on mute. And then we have the receiver side. So we go to the input stage. We have our RF analog to digital converter. It goes into this huge FPGA we have on the board. Have some acquisition memory locally. We have some fast memory for streaming out. And then we have the programmable FPGA. So what we're going to look at is how an RF DAC works, how RF ADC works, and then how to program this FPGA. We can transfer data or waveforms off the instrument very fast as well, because the instrumentation sits on a PCIe Gen 3x8 bus. This is equivalent to the bus that you will find in a modern PC, and the modern PC or your PC treats a Proteus card as it would treat a GPU card or a graphics card within the instrumentation. So this instrumentation sits on the bus of your PC, albeit this is in a separate measurement rack unit that is connected through an extender cable to your PC. But we get the speeds that are required to do very fast transfer of data in and data out. On board the instrument, we also have 16 gigasamples of memory, so we can store very large sequences if we choose to. Let's look at specifically the DAC system of the instrumentation. A regular arbitrary waveform generator has some kind of RAM system, and you would have segments, and you play different segments in different orders, and that would all be orchestrated by the FPGA, and you would play out through the DAC. This is great when you just want to generate pulses or shape pulses that we'll look at. But the difference between a Proteus arbitrary waveform generator and an off-the-shelf, a regular off-the-shelf arbitrary waveform generator, is that within this DAC here, we have a real-time complex upconversion system. So from our FPGA, we're essentially feeding I and Q pairs. We have some filtering or some interpolation here. And then we have the complex mixer, and we have the NCO, which stands for numerically controlled oscillator. So this in digital terms is the name for your local oscillator. So we feed a sine wave and a cosine wave to the complex mixer to get our I and Q components and sum them to a signal, and then we have 1/sin x filtering here, and then it goes out through our high-speed DAC. Optionally, you could add some filtering and some amplifiers. For example, in this picture that I did of a 8 gigahertz pulse, Gaussian pulse here, you can see I've got a mini circuits filter. Then I'm feeding our 10200A 1-watt amplifier to get to a desired amplitude. So this instrument that is a companion to this has 20 gigahertz of bandwidth, and again of about 10 across that bandwidth. So useful addition. So you can see here now, instead of using the regular arbitrary waveform generator and a signal generator, we've combined that with the complex mixer and NCO as part of the overall instrumentation. Here's an example. So I generate a square wave or a pulse on, as you would do in this typical circuit here. And then I switch on the IQ modulator within the chipset, and immediately you can see this pulse is now modulated. And if I do an FFT of the spectrum, this whole piece of software is available on our GitHub by the GitHub site. You can see we have the center frequency of gigahertz. Because we turn the pulse on rather rapidly and turn it off, we have a lot of spectral components here. And so in real life, we want to probably clean that up and have a more elegant way of switching on the pulse. So I've refined the pulse a little and made it into a Gaussian pulse here. And you can see the spectral spread is far limited because we don't have the abrupt start and stop. We can control the phase of this Gaussian pulse. very accurately because we're sampling at 9 gigasamples per second, essentially, in a lot of these measurement scenarios. So if you want to accurately go from pi to pi over 2, for example, this can do it very coherently, not just on one channel pulse to pulse, but across 16 or 24 or 38 channels if you choose to. So it's a very coherent system. In this example here, I have the digitizer digitizing at 5.4 gigasamples per second. So you can see the maximum frequency is 2.7 megahertz here. One thing that I can do, and so I've generated this signal at 1 gigahertz, and I'm generating that signal in the first Nyquist zone of the arbitrary waveform generator. What we've allowed in our arbitrary waveform generators is the ability to use multiple Nyquist zones to get to the required frequency. So I have a signal here at 1 gigahertz, and say I have my clock set at 8 gigahertz, for example. I would see that image at 8 gigahertz minus the original frequency and 8 gigahertz plus that original frequency, so 7 and 9 gigahertz. Conversely, you can also see it on the second Nyquist zone here, and so it would be 16 plus or minus 1 gigahertz, and you can go on and on. However, the trade-off is, of course, the amplitude of the signal goes down the higher up you go in the Nyquist zones, and this usually follows a sine x over x amplitude envelope. So that's just one thing to look out for. But we've done measurements at 13 gigahertz with a 9 gigasample unit, so operating it in the third Nyquist zone has been reasonably easy for this type of instrumentation. Conversely, if we look at the digitizer in the unit is it's a if you have it in 2-channel mode, each digitizer comes with 2 channels. It's 2.7 gigasamples per channel, but you can interleave those to do to 5.4 gigasamples, and you can see here in this spectrum display that I've got the 5.4 gigahertz signal. But just like we showed with the arbitrary waveform generator, we can undersample in this case and measure a signal in different Nyquist bands as well. And so what I've done in this next slide, using the same principles as I discussed here, essentially, I used our Lucid analog RF signal generator. And so I generated a 1 gigahertz signal here in the first Nyquist zone. And then I generated a 5 gigahertz signal, which ends up in the second Nyquist zone of the instrumentation. You can see this amplitude and this amplitude in the first and second Nyquist zone are almost the same. And then I skipped a Nyquist zone, but went straight to the fourth Nyquist zone, and show here I'm generated 10 gigahertz signal with the arbitrary wave, with the Lucid RF signal generator putting into the digitizer. And you can see we've got a 20 dB 15 dB drop in amplitude now, but still there's a carrier there that we can resolve or amplify. So using the instrument both in the arbitrary waveform generator multiple Nyquist zones or undersampling using the analog digital converter gives us a lot of flexibility and allows us at a reasonable cost point to be able to create signals at, for 4 gigahertz control and 8 gigahertz or 9 gigahertz of measurement. So it's a very versatile system for generating signals at different RF frequencies directly without the need of an RF up converter. Let's look at the IQ modulator here, and it's a 12-bit ADC. It's 16 bits, by the way, on the digital to analog converter. And again, built into the silicon, as with the as with the arbitrary waveform generator side, our Digitizer has, again, an NCO, it has an IQ mixer, it has some filtering. You can bypass this if you choose to digitize directly and just get magnitude data. But when you use this system here, you're feeding the FPGA with I and Q components similar to the I and Q that you used to generate the signal. We use bypass mode. It is magnitude only, but we do provide some data reduction capability for the rest of the FPGA system through a decimator here in the FPGA. So that is a good segue to go into what's in the FPGA. So far, we've talked about the technology we developed to do the acquisition, and that's our RF ADC. We get in-phase and quadrature components coming out of that. And then at the beginning of the presentation, I talked about the playout, or the digital to analog converter. So we get the in-phase and quadrature components. So traditionally, this used to be one instrument, this used to be another instrument, and the center part never really existed. So we've joined all three of these blocks up now to produce an easy to program real-time FPGA processing system. So if I make an acquisition, I can do some kind of data reduction. In this case, it's a digital down converter. If I want to do a filter, I can select the number of taps on an FIR filter. If I want to do some processing like add, average, subtract, multiply, FFT, IFFT, I can do it here in the math section. Then I want to take an action, because we're not doing all this just for fun. We want to be able to play out a new signal. So this is a decision here. So if X equals Y, let's make a decision. If X does not equal Y, let's make another decision. So this is what the action part of the FPGA programming language does. And then, of course, the waveform generation part is here, and the memory associated with all the waveforms that you can select after the decision. Then we have the in-phase and quadrature going to the DAC, and as I said earlier, you can plonk those in one of the many Nyquist zones, or you can use it in the first Nyquist zone and create a control signal. And this is a totally coherent system from acquisition through to play out. It's deterministic, and we have you'll be able to track the phases between each waveform, either on the acquisition side or the playout side. Now, in the example I'd like to go through today, I want to show a few things here. And it's a simple example. I'm going to acquire a signal. I'm going to say, does it exceed a threshold? If yes, select waveform from memory 1. If no, select waveform from memory 2, and then play out the waveform. So this is our very simple flow chart. One of the things that we did to simplify FPGA programming is use the Skippy programming language to be able to send commands to the FPGA that would be stored and then executed once you apply a trigger or a go command. And in this example here, I'm using mainly the task list, and I'll go on to what the task list is in a minute, but a lot of these functions here are in the DSP subsystem. And we also have the Digitizer and AWG or source subsystems as well, but I'll cover those later. So if you send this simple Skippy command as by way of an example, DSP, FIR, select, bypass on, that means we're not going to use this function. And this goes back to the reason why we call them decision blocks, because they're essentially they're blocks of FPGA processing capability that you choose to use, configure, or not use. So earlier I said, let's look at the FIR filter so we can bypass it, so we can go around it. Or we can say, we're not going to bypass it, we're going to use it. And then you're going to say, well, what type of filter do I want? So you program the taps in this filter and you can create a filter. because this is a high-speed FPGA system, it's very difficult to write the code from scratch, because every part of code that you add, if you were taking this on yourself, could contribute to a timing error within the FPGA. So to simplify it, we've created these blocks, so you can either use them or not. So you can have A plus B in math and decision and waveform, etc. So I gave an example of that. Let's dive into this in a little more detail. I'm going to create something called a task table to do this part of the flowchart here. And essentially, I'm going to have a starter task. I'm going to say trigger CPU, which is essentially free run trigger. I'm going to play out a DC waveform. Then I'm going to go to task 2. Task 2, it says play out a Gaussian pulse. Within task 2, it says trigger the DAC, enable an acquisition. So it goes off to the Digitizer subsystem and tells the Digitizer to wait for a task table trigger, or the Digitizer system set up waiting for this trigger. And then we digitize the signal and we pass the acquisition to the DSP subsystem. And this is where we do, does it exceed a threshold or not? Return a 0 to task table if not exceeded, return a 1 to task table if exceeded. So we play a Gaussian pulse. We trigger the Digitizer. Digitizer acquires it. Has it exceeded the threshold? Yes. Has it not? No. So on DSP return 0, go to task 4, play a Gaussian pulse. On DSP return it to task 1, go to task 3, play a square wave pulse. So you can see this is a very simple example of how we'd program the FPGA. So we load all these commands in using the Skippy language into the FPGA, and then it's basically hard-coded into the FPGA, waiting for you to kick off the whole system. After this, no other user intervention is required, although we can pull waveforms out at any time or pull header data out, such as when we digitized, at what time we digitized some stuff, length of waveforms we digitized, etc. So if I look at how we would program the FPGA, we use, like I said, the Skippy language. So that is everything within these quotes here. So I'm going to say on channel 1 of the Digitizer, create a table. The length of the table is going to be 5. And so I've got 1, 2, 3, 4, 5 different tasks here, and the maps to what we're doing here. And by the way, I can have a task table assigned to every single channel, and each task table will run step by step, aligned with each other, so we can make coherent decisions based on what type of signal that we receive. So as we go here, I had segment 2 defined as a DC level, and then we go task composer next 1. So that's the next one we go to is task 2. Enable CPU, do idle, go to task 3. So this is the key one here, which was this center one here. So you can see in the language, task composer, D-trig on, issue a trigger to the ADC. So that goes off to the digitizer, and there's a separate part of the code that has the digitizer set up waiting for the acquisition and has the memory allocated to store the acquisition. And then this is here is where we would use make the decision here. Next, if digitizer signal 1, go to this task. If it's 0, go to this task. So just let me move. I've got a box blocking my screen here. So DSP, if it exceeds, return a 0 if it exceeds, return a 1 if it's not exceeded. Return a 1 if it's exceeded, return a 0 if it's not exceeded. So so if I run the scenario now, I've programmed into waveform memory 3 waveforms, a Gaussian pulse, a square wave, and DC levels. And then when I run the system, if the threshold's exceeded, then play a square wave. So we played out this one initially, which was the Gaussian pulse here. And then we exceeded, so it said play out the square wave. And then we looped it round again and changed the threshold so it wouldn't exceed. So if it didn't exceed, it just played out the Gaussian wave again. So the key thing to understand about this is that in this scenario, the turnaround time is 288, about 290 nanoseconds to do this, and there's no user intervention required as you go through this process. This is all programmed into the FPGA, and you can make these decisions by configuring the decision blocks within the task table. I just did a simple example today to simplify it because I'm presenting to many people through a webinar, but there's different operational modes. You can do this in real, or you could do it in complex, as I showed with the earlier on in the DAC modes and ADC modes. We have demodulation and down conversion, DDCs, up conversion, DUCs. These are all our data reduction techniques. As on the digitizer side, we have a complete set of filters in the FIR. You can define the taps or the bypass. In math, you can scale, offset, do cross correlations, rolling averages and integrations. And then decision mapping. And this is a very important one because in a regular quantum computing system, you may want to generate many channels of pulses, but you may only want to digitize one or two measurement points. And so the digitizer not only controls a single channel, which I showed in this example here, you can have this decision go controlling different channels or different modules within the same PXIe modular system that the arbitrary waveform or arbitrary waveform transistor is embedded in. So that's a key thing as well. So you can make one measurement and control, say, 16 different waveforms or 16 different channels. If you want to write your own FPGA language and not use the simplified language that we created, we have what we call the shell option. So this is a binary file that contains interfaces to our external IOs, and we provide a top-level Verilog file. And you can create your own arbitrary waveform generator and digitizer and write your own program to go within it. Much more flexible, much more tuned to what more advanced experiments would like to do. So that's a capability beyond the decision block system here. This requires FPGA skill and a lot of patience with being able to create FPGA code that contains no timing errors, for example. So as I approach the conclusion now, we have this block diagram that I just talked about. So we have RF DACs. We can generate signals. You know, we've using multiple Nyquist zones gone all the way up to 13 gigahertz. We can digitize. I showed an example of digitizing at 10 gigahertz. We have this easy to use programmable language that we call decision blocks. Choose what decision block you want to do, set up the decision block. We can stream memory, we can stream waveforms in and out of the instrument very fast using this PCIe backplane. Plus, you know, this is a 4-qubit control module. We can stack these along, and I'll show that in a different slide. So this is 4, you put another one next to it, it'll be 8, 16, 32, 16, 20, 8, 4, 8, 12, 16, 20, 24, etc. It does come in multiple form factors as well. So here we look at a single channel, and I've already talked about its modular. You get very large pulse library. With the FPGA, we can do fast qubit control. But if you look at the form factors as well, we take this module here, and you can see it can go in what we call the PXI-E infrastructure. And so here's a module. This is an AWT. So it has the digitizer. This is an AWG, so it doesn't have the digitizer. So this row is essentially missing. So you can put that in what we call the desktop version and the benchtop versions. So these two instruments are the same. This doesn't have a screen. This doesn't have the screen or the keyboard, so it's a little cheaper, but both these instruments inside it have a controller computer. They're server based. You can have multiple users accessing the instrumentation across the LAN, and it's a very good system if you're trying to control probably multiple experiments from one arbitrary waveform generator, or you've got instrumentation set apart in distance, for example, if you're working on a linear accelerator or something like that. This is what we call the high speed one. So if you're doing a qubit system with 32, 64, I don't know, just keep going up 300 qubits, then stacking these modules here coherently within this chassis is the way to go. And because this sits on a very fast PCI bus, we get very fast transfer rates. So it comes in three form factors, but the measurement cards are essentially the same. Transfer speed slightly differs. This has a slower backplane than this, for example, but this has LAN control or USB-C control, where this is straight PCIe connections to your computer. And just to wrap up, we have the Proteus family that I talked about. We also have a line of RF signal generators. It's a building block system, so everything is derived from a module. You put the module in this portable unit, put a screen on it. It's waterproof, it's battery powered. You can use it on your bench or out and around in the field. You can put up to 4 modules in this rack mount system. You can add a screen and a keyboard to the rack mount system and have a 4-channel signal generator. It's quite a good system, and if you ever follow the signal path video blogger, he has a very good review. So just type into Google signal path Tabor and a review of this modular system will come up, and the quality of the signals and how well it works, and he gives some measurement examples. And so if you want to use it in the traditional method, I'm just going back loads of slides now. With the signal generator, lower frequency ARB, we supply that as well, because the Proteus comes in 1.25, 2.5, and 9 gigasample options. So at various price points. So you can either use it direct to RF or with a local oscillator and up converter. And then we have a range of amplifiers if you need to amplify the signals, including the new amplifier that I talked about, the 10200, which has 20 gigahertz of bandwidth and 10 dBs again, and allows you to get power of up to 30 dBm. And I thank you for your patience. We've just completed the seminar at 36 minutes, so I'll open it up for any questions.